Hi everyone. In this lecture I want to take you pretty much to the edge of what we know at a fundamental level about physics and talk about a little bit beyond that edge, ultimately a little bit of string theory, cosmology, things like that. So, we left off discussing about how the protons and the neutrons in the atom are actually composed of more fundamental particles called quarks, and how we have four basic fundamental levels, if you will, to this new kind of periodic chart, if you will, of the elementary particles' nature. We have the electron and its partners, the neutrino and its partners, the up and down quarks and its partners. Kind of going to the left on this chart, you have this generation of particles is called the first generation, and these are the least massive of all. So in order to get up here into the second and third generation of particles, you have to increase the amount of energy. And also what that means is that, in order to actually experience these, you have to have stronger atom smashers. This down here was the last of these fundamental 12 particles to be discovered. And so what happens is that these particles actually tend to decay through intermediate reactions down into particles on this side of the chart. Now this decay is actually the exact same decay that occurs in the neutron. See, these decay events are actually manifestations of what we were calling the weak nuclear force. And if you think about the last lecture, I left that out completely. We talked about how we've got the electromagnetic force, and we have a satisfying theory called quantum electrodynamics. Introduced the strong theory and its corresponding color charge mediated by gluons. We have a quantum field theory that explains that. Well, what about this weak nuclear force that's behind the decay of the neutron? Does it have a corresponding picture? And the answer is yes. And that is why on this chart we've got three types of bosons. A photon, which is a particle of light, mediates the electromagnetic interaction. The gluon, which mediates the strong nuclear force, exchanging color between the particles. Now we are going to introduce something called the weak boson. The weak boson mediates this weak nuclear force. And so essentially we've got 12 of these fermions, which make up matter in the universe as we know it, mediated by three fundamental bosons. And so we've got 12 plus 3, making 15 particles. Now sometimes people add a fourth for gravity. Gravity, a quantum field theory for gravity does not exist at the moment. In fact, it's one of the subjects later in the lecture, how are physicists grappling with this idea of incorporating gravity into this basic framework that's so successful at explaining everything else. And that's an open question. These numbers roughly represent the interaction strengths between the various particles. So remember, these 12 particles interact, exchanging these three different particles at different rates and at different times. And that's what these numbers represent in a rough type of way. This chart, along with the quantum field theory, those Feynman diagrams that we were discussing, this framework is called the standard model of particle physics and is basically the root and foundation of the physical world as we know it. There is no known reaction that's ever been experienced in any kind of atom smashing experiment or seen in astronomical phenomena or anything. There's effectively no known experiment that cannot be explained with the standard model of particle physics. And that's an extremely exciting situation to be in. We really have a fundamental understanding of how the world works. On the other hand, it's also extremely frustrating because we know there's a missing gap called gravity, and yet we really don't have any kind of experimental clues to figure it out because this thing's so successful. And so how to move beyond the standard model and incorporate gravity, which we know has to happen, is quite a challenge. Effectively, we're working blind because we don't have experiments that are strong enough to push beyond the limits, the known limits of the standard model. Also, the recent discovery of the Higgs boson is a component of the standard model, which actually kind of completed the whole structure. And so physicists were pretty confident it would be discovered. Until it was, though, there was still this nagging question: will it be discovered, will it not, what if it doesn't, different things like that. But people are fairly confident that it does exist, and that is something we'll talk about in future videos.